Today, we explore one of the most fascinating phenomena in modern physics, quantum coherence in supercooled nanodroplets. We will investigate how nanoscale water droplets exhibit quantum behavior that defies classical thermal physics. Let's begin by understanding what supercooled nanodroplets actually are. Supercooled nanodroplets are tiny water droplets that remain liquid even when cooled below the normal freezing temperature of 0 degrees Celsius. These droplets are incredibly small, ranging from 1 to 100 nanometers in diameter, about 1,000th the width of a human hair. Here we see a representation of a nanodroplet containing hundreds of water molecules arranged in a quasi-spherical structure. The number of molecules n in a droplet scales with the cube of its diameter d divided by the molecular size of about 0.3 nanometers. For a typical 10 nanometer droplet, this gives us approximately 30,000 water molecules, which is mesoscopic, between microscopic and macroscopic scales. Now let's understand what phonon-like oscillations mean in this context. Phonons are the quantum mechanical description of collective vibrations in a material, similar to how photons describe light. In a nanodroplet, molecules oscillate in coordinated wave-like patterns, creating phonon modes that propagate through the structure. The phonon frequency omega equals the speed of sound versus s times the wave vector k. In liquid water, the speed of sound is approximately 1,500 meters per second. For a 10 nanometer droplet, this gives phonon frequencies on the order of 100 gigahertz, or 10 to the 11 hertz. Here's where things get truly mysterious and fascinating. According to classical physics, these oscillations should decay rapidly due to thermal fluctuations and energy dissipation. This graph shows the dramatic difference. The red curve shows the expected rapid decay, while the blue curve shows the surprisingly long-lived oscillations actually observed. You might ask, what determines how quickly thermal relaxation should occur? The thermal relaxation time, tau thermal, is given by Planck's constant h bar divided by Boltzmann's constant Kb times temperature T. At typical supercooled temperatures of 250 Kelvin, this gives a thermal timescale of only about 50 femtoseconds. Yet the observed coherence persists for several picoseconds, more than 20 times longer than thermal relaxation should allow. To understand this phenomenon, we need to grasp the basics of quantum coherence. Quantum coherence means that different parts of the system maintain definite phase relationships, like synchronized dancers. In a coherent state, all quantum phases point in similar directions, like these arrows showing aligned phase vectors. Mathematically, a coherent state is a superposition where all components have well-defined relative phases phi I. Decoherence is the process where interactions with the environment destroy these delicate phase relationships. The decoherence time tau dec is h bar divided by coupling parameter gamma times kBt. Let's examine why quantum effects might appear at these mesoscopic scales. You might wonder, aren't quantum effects supposed to be limited to individual atoms? Not at all. Quantum mechanics allows for collective states involving thousands of particles acting coherently. The de Broglie wavelength, lambda dB, equals Planck's constant h, divided by the square root of 2 pi times mass m times kBt. For a water molecule at 250 Kelvin, this thermal de Broglie wavelength is about 0.2 angstroms. However, collective phonon modes can have coherence lengths much larger than individual molecular wavelengths. The coherence length, GSA, is the sound velocity times the coherence time tau. With 1 picosecond coherence time, this gives a coherence length of about 1.5 nanometers, spanning many molecules. Let's analyze the relevant energy scales to understand when quantum effects dominate. The phonon energy is h bar times the angular frequency omega. For our 100 gigahertz phonons, this gives about 10 to the minus 22 joules, or about 0.7 milli-electron volts. The thermal energy at 250 Kelvin is kBt, approximately 21 milli-electron volts. The thermal energy is about 30 times larger than a single phonon energy, suggesting classical behavior should dominate. However, the key insight is that many phonons can couple together, forming a collective quantum state with enhanced stability. This diagram shows the energy hierarchy. Thermal energy dominates, but collective phonon and zero-point energies create a quantum substrate. Confinement in the nanodroplet plays a crucial role in quantum coherence. When waves are confined in a small space, only certain discrete modes can exist, leading to quantization. The allowed wave vectors kn equal n pi divided by the droplet diameter d, where n is an integer. This gives discrete phonon frequencies omega n equals sound velocity times n pi over d. These horizontal lines represent the discrete energy levels of confined phonon modes, like notes on a musical scale. Having discrete levels rather than continuous energies reduces the phase space available for thermal scattering, protecting coherence. This is analogous to how atoms can't radiate energy continuously, but only in discrete quantum jumps. The persistence of coherence suggests genuine quantum correlations across the entire droplet. The system forms a many-body quantum state, where molecules are quantum mechanically entangled. The total state cannot be written as a simple product of individual molecular states, indicating true quantum correlations. This network represents quantum entanglement. Changing one molecule's state instantly affects the others through quantum correlations. How can scientists actually measure these subtle quantum correlations in practice? The answer is ultrafast time-resolved spectroscopy, using femtosecond laser pulses to probe the coherence. The signal S of t measures the correlation function, showing how properties at time 0 relate to those at time t. Persistent oscillations in this signal directly reveal the coherent quantum dynamics lasting picoseconds. The quantum coherence shows fascinating temperature dependence. This graph shows how coherence time decreases exponentially with increasing temperature, as thermal noise destroys quantum correlations. The coherence time follows an exponential law, tau 0 times exponential of minus t over a characteristic temperature, Tc. Below about 250 Kelvin, we enter a quantum regime where coherence times become significantly longer than thermal times. Above 270 Kelvin, we transition to a classical regime where decoherence happens on thermal timescales. The crossover temperature represents a genuine quantum to classical phase transition in the droplet dynamics. The quantum coherence depends critically on the droplet size. If droplets are too small, with only tens of molecules, individual quantum fluctuations prevent stable collective modes. If droplets are too large, with millions of molecules, they behave classically, and thermal effects overwhelm quantum coherence. This curve shows a sweet spot around 10 to 20 nanometers where quantum coherence is maximized. The optimal size scales as the square root of h bar times sound velocity divided by kBt. At 250 Kelvin, this predicts an optimal diameter of about 15 nanometers, matching experimental observations. The underlying mechanism involves quantum zero-point motion. Even at absolute zero temperature, quantum mechanics requires that systems retain zero-point energy in motion. The zero-point energy equals 1/2 h bar omega for each quantum harmonic mode. These quantum zero-point fluctuations actually help stabilize the coherent phonon modes against thermal noise. This wave represents zero-point quantum fluctuations that never cease, providing a quantum mechanical baseline that resists thermal disruption. The quantum mean square displacement equals h bar over 2 meters omega, a purely quantum result with no temperature dependence. Counterintuitively, this quantum noise actually protects the coherence against thermal noise through quantum Zeno-like effects. The unique hydrogen bonding network in water plays a crucial role. Water molecules form strong tetrahedral hydrogen bond networks, creating a highly correlated structure. Each central water molecule forms hydrogen bonds with 4 neighbors in a tetrahedral geometry. Each hydrogen bond has an energy of about 20 kilojoules per mole, or roughly 0.2 electron volts per bond. This hydrogen bond energy of 0.2 electron volts is much greater than the thermal energy of 0.02 electron volts at 250 Kelvin. These strong bonds create collective coupling that ties molecular motions together, enabling coherent dynamics across many molecules. The specific network topology of hydrogen bonds actually enhances quantum correlations through constructive interference effects. How do nanodroplets compare to other quantum systems? This comparison shows coherence times. Atoms maintain coherence for seconds, superconductors for milliseconds, Bose condensates for seconds, while nanodroplets show picosecond coherence. What makes nanodroplets remarkable is they exhibit quantum coherence at relatively warm temperatures and high densities. They represent a bridge between the microscopic quantum world and the macroscopic classical world. How do scientists experimentally detect these quantum coherence signals? The primary method uses pump-probe spectroscopy with femtosecond laser pulses to create and detect coherent oscillations. A pump pulse excites the droplet, then a time-delayed probe pulse measures how the coherence evolves over time. These experiments achieve time resolution of about 10 femtoseconds, fast enough to capture the coherent dynamics. The time-energy uncertainty principle limits resolution. Delta T times delta E must be greater than h bar over 2. The detected signal shows oscillations at the phonon frequency, with a slowly decaying envelope revealing the coherence time. Theoretical understanding of this phenomenon faces significant challenges. Standard classical molecular dynamics simulations are too classical and completely miss the extended quantum coherence. Full quantum mechanical treatment is computationally intractable for systems with 30,000 atoms. The quantum Hilbert space dimension scales exponentially, reaching 10 to the 10,000 power for these systems. Successful approaches use hybrid methods that treat select phonon modes quantum mechanically on a classical molecular background. Open quantum systems theory provides a rigorous framework for describing quantum coherence coupled to thermal environments. The density matrix rho evolves according to minus I over h bar times a commutator with Hamiltonian h, plus a Lindblad superoperator L describing decoherence. These findings have profound implications for quantum biology. This raises a tantalizing question. Could similar quantum coherence effects occur in biological systems? The answer is possibly yes, especially in protected nanoscale environments within cells. Protein cavities and membrane pockets could provide similar confinement and protection from thermal noise. There is already evidence for quantum coherence in photosynthetic energy transfer occurring at biological temperatures. Quantum tunneling and coherence have been proposed to enhance enzyme catalysis rates beyond classical predictions. Nanodroplets provide a simpler, more controlled model system to study the principles governing biological quantum effects.